This is a production of Cornell University.
Okay, infiltration in a nutshell. If we start talking about what is transporting these things, we really have to start talking about the pores. And we've talked about this, like you heard me say micropores and macropores, but this is just sort of the table for it. Interaggregate pores versus intra-aggregate, macropores versus micropores. Macropores are the pores between the aggregates or between the individual grains, particles. Micropores or interaggregate pores are the ones that are inside the aggregates. The macropores are large. They're important for transport and water flow and gas exchange. This is where the air moves as well. Micropores, smaller obviously, they have little contribution to water flow, huge contribution to water storage. They also have very little contribution to gas exchange. There is gas exchange and water exchange, but because of the nature of these pores, the exchange of water and oxygen is extremely slow. Infiltration events, they're not going to be driving a lot of the exchange. They're going to be sucking it in and just holding it. Okay, so where do these pores come from? Roots, as they decay, animal operations, animals moving through boring, okay, soil drying, shrinking and swelling, creating cracks, as well as the freeze-thaw cycles. This is also, all four of these are also have a huge influence on how structures are created. So you can see that there's a strong relationship between them. As these structures are created, we're going to start making these pores, and then we'll start making sort of the micropores inside the aggregates, all due to how these structures are created. So huge relationship. Okay, I think at this point I'm probably beating a dead horse. Small pores hold water well. They restrict aeration. Large pores hold water poorly, and they permit the free movement of air. Okay? Take-home message here, after the idea that we're talking about infiltration in a nutshell, the soil is a three-phase system. The soil air connects to the atmosphere, the soil solutions, solvents for the reaction, and the soil atmosphere with the rain, and then the soil solids basically act as reserve for the nutrients. These are all interacting with each other. Okay, do we feel comfortable with this? Oh, question, go.
Did you say that inter-aggregate was the...
Inter versus intra.
Yeah, which one was the bigger one?
Oops, skip right over it. So these are inter, sort of like think of it as an intramural versus the rest of the sports. Intramural is within, so intra-aggregate is within. Inter is between, or inter is between, so between the aggregates. Between the aggregates versus inside the aggregates. Okay, it should also, when we say aggregates, this also, inter also means like sand grains and things like that. It's not just the aggregates. Rocks, gravel, that kind of stuff. Those large pores. Okay, we good? All right. All right, which brings us to this. Now, this is actually a transitional slide. This is actually talking about two things, but I'm using the slide right now to talk about infiltration. This also starts talking about subsurface flow, okay? But these two lines basically represent a wetting front. This is the soil depth up to the surface there, and this is the soil water content. This is theta. This is a new term, and I'll explain it in a moment. But theta basically represents how much water is in your soil. It's a measure of the percent, okay? So if we have a 1-hour rain event, okay, the water line, so you started with water that was here, basically had like 10% water content, okay? If it starts raining, you can see how the water moves through the system, okay? We're visualizing sort of mass flow here. It's sort of coming as a wall of water, okay? After 3 hours, you can see that that wetting front is dramatically farther down into the soil, okay? And you can see that the amount of water content increases with depth as you have a longer time period. Does that make sense? And this is generally how we visualize soil water movement in soil. Now, it's not quite true, but in general, you get the idea. If it starts raining, the water's going to start infiltrating, and if it stops raining, it's only going to infiltrate a certain amount. Okay? At which point, intersoil activities will start taking control, and it will start moving the water more. But after a rain event, you sort of see the waterfront. Okay? If the rain event is longer, the waterfront is going to be deeper. Make sense? Okay. The other thing that we're talking about here is this theta. And I'm going to introduce this now because we're going to be talking a lot about this tomorrow or Wednesday. Theta is basically a volume. It basically means volumetric water content. Okay? And it's a measurement of the volume of the water over the volume of the total. Now, often when people think about this, well, you know, if I got a saturated soil, I got 100% water in the system. And that's not true. Okay? Remember me drawing that pie chart? Remember soil, we got to think of soil as a volume, right? Okay, here's my entire soil. Okay? 50% of this, though, is solid material. So a saturated soil is not 100%, it's 50%. It's got 50% of the total volume is water. Does that make sense? This is where the water is, only in this part. So when you see something like this, my theta saturated of a sand is basically 40 to 50%. That makes sense now because you have to take into account that other percentage of that total volume. Okay, now sands, 40 to 50% theta, that's a saturated soil. Clays, 50% or more. What's going on there? You would think, I mean, if I got total volume and, you know, I'm packing this material, one would think that, well, you know, they should basically be the same. Why am I getting more water in a clay system versus a sand system? The micropores, basically it has to do with how the packing. So we're looking at the clays, lot smaller pores, but the way the clay packs, potentially you have more volume. So if you look at this pie chart, the thought is, if this is a sandy soil, the part of the sand represents more like that much. If you're looking at a clayey soil, the clay represents more like this part. So there's more volume, pore space, available in a clay to be filled up with water than there is in a sand to get filled up with water in the same given volume. And that has to do with just basically the differences of the material. Go.
What is it like in a peat system?
What is it like in a peat system? A peat system, when it gets saturated, you're looking at 87, 90%. Because you got to imagine how peats pack. Okay, when a peat, it's a fibric material. This given volume may have a very small percentage of that given volume actually being peat. But the peat has filled up the material because it has a huge amount of pore space. Does that make sense? So if I had a peat up there and it said saturated peat, you know, you could be up to, you know, depending on the porosity, you know, it could be 80, 90% theta, a theta of 8, a 0.8. Okay? Does that make sense? Or 80%. Does everybody feel cool with that? Go.
In the equation, in the denominator, is it volume of soil and volume of pores?
This says volume total, volumes of the soil, the solid, plus the volume of the void space, the pores. Okay? This is still the volume of the water, though. Right? So when we're figuring out the theta, we're only interested in this part of it for that. That's the volume of the water. Okay? And as this soil dries, the theta is going to go down. You know, as evapotranspiration happens, the amount of water that's in that system is going to go down, and therefore the theta is going to go down. This is a saturated system where there's no oxygen in the system. That's where these numbers come from. Okay, do we feel comfortable with this? Yeah? Okay, we're going to stop here. We'll start in again on Wednesday. We'll be talking about subsurface flow. You guys have a great rest of the day.
This has been a production of Cornell University, on the web at cornell.edu.